We are the Small REU. I'm Annika, and I'm here with Zeus, Drew, Astrid, and Santiago, and we're presenting our joint work with Stephen Miller and Matthew Phang on a generalization of Fibonacci sequence, which we call S-legal index difference sequences. So today we're going to motivate how we found these sequences, define them, and then talk about what we've done and what we hope to do this summer. So for the remainder of this talk, we're going to index the Fibonacci numbers beginning 1, 2. And it's a theorem of Zeckendorf that every non-negative integer has a unique decomposition as a sum of non-consecutive Fibonacci numbers. So as a result of this, there's an alternate equivalent definition for the Fibonacci sequence, where we let the nth Fibonacci number be the smallest positive integer, which cannot be written as a sum of non-consecutive previous Fibonacci numbers. So just to illustrate that this really does give us the Fibonacci numbers with this alternate definition, for the first 3 Fibonacci numbers, this is pretty easy to see that it's just going to be 1, 2, 3. For example, F3 will be 3 because it's the smallest positive integer, which cannot be written as a sum of non-consecutive terms in 1 and 2, because 1 and 2 are consecutive. So the next one has to be 3. This continues to give us the Fibonacci sequence with this process. So F4, the smallest positive integer, which cannot be written as a sum of non-consecutive terms in 1, 2, 3. The way we will compute this is by writing down all of the possible allowed sums in this set, which will be just the singletons 1, 2, and 3, and then 1 plus 3, because those are non-consecutive. And then we just have to ask, what is the smallest number not in this list, which will be 5. The same for the next number, we just write down all of the possible allowed sums by taking the sums of non-consecutive things, and then look at the smallest thing not in this list. Here, everything up to 7 is in the list, so the 5th Fibonacci number will be 8. So we can kind of represent this geometrically by putting the Fibonacci sequence in a 1D array of boxes and saying a legal decomposition into these Fibonacci numbers will be a sum that does not have summands that correspond to boxes sharing an edge. So it's a sum of boxes that do not touch in this picture. But this 1D array of boxes is pretty boring. So we want to ask, what is another cool arrangement of boxes related to the Fibonacci numbers? And of course, the natural answer to that is the Fibonacci spiral. So we have the Fibonacci spiral. It looks a little bit funny. This is because instead of making larger and larger squares, we have these more skinny rectangles. But in terms of adjacency, this is completely equivalent to the Fibonacci spiral, but allows us to display it more compactly. So now we want to do something similar to Zeckendorf's theorem with this Fibonacci quilt. So this is the Fibonacci quilt sequence. So we define the sequence to be the nth term is the smallest positive integer, which cannot be written as a sum of non-adjacent previous terms. But here, non-adjacent means, adjacent means that the boxes share an edge in the quilt. So to illustrate how we compute this sequence, you can trust me that the first 5 terms will be pretty simple to compute. They'll be 1, 2, 3, 4, 5. And now we want to make the next term. So to do this, we'll write down all of the possible legal sums using 1, 2, 3, 4, 5. And here legal means, again, that the boxes corresponding to those numbers are not adjacent in the quilt. So here, for example, 6 being written as 2 plus 4 is legal because the boxes corresponding to 2 and 4 are not touching in the quilt. And now we just ask, what is the smallest integer not appearing in this list? Well, it's going to be 7. So the next term in the sequence will be 7. To compute the next term of the sequence, we again write down all of the possible legal sums using the previous terms, which are written here, and find the smallest positive value that is not written in this list, which will be 9. Here, to point out, 8 can be legally decomposed as both 3 plus 5 and 1 plus 7. And this will continue to be true. There'll be lots of numbers with non-unique decompositions, unlike second-order theorem, where the decompositions are unique. But using this definition of the Fibonacci quilt sequence to calculate terms is pretty slow, because every time we want to make a new term, we have to write down all of the possible legal sums of the existing sequence. But it turns out that for the Fibonacci quilt sequence, a theorem of Miller and Newlin showed that the Fibonacci quilt sequence follows this positive recurrence, just this linear recurrence. Not positive. So we want to define a similar quilt sequence to the Fibonacci quilt sequence, but beginning with a different geometric pattern. So here we defined the triangular quilt sequence, where we began with the Poitevin spiral, which is shown here, of just these triangles spiraling outwards. We define it completely analogously, where Tn is the smallest positive integer, which cannot be written as a sum of non-adjacent previous terms. But here adjacent, two terms are adjacent if their boxes share an edge now in the Poitevin spiral. And we can do the same thing where we try and compute the terms of the triangular quilt sequence. But again, this is computationally expensive because we have to go through and write down all the legal sums. But we are able to compute the first 50 terms, which are appearing here. And the natural question, once we have these terms, is, does it follow a recurrence? What recurrence would this follow? Maybe it would be like the Fibonacci quilt, where it's a very nice recurrence. I will pass it on to Drew, who will talk about what we did next.
All right, thank you. So our motivating question, as Annika said, is to try and find some recurrence relation or other way to better understand this pattern we see in the triangular quilt sequence. From just our initial playing around with the initial terms, we found that there was no clear recurrence relation that fell out right away. And moreover, when we just plug this into OEIS, we found that this sequence did not match any of the ones already on there, which means we might have stumbled upon something new and interesting that we want to understand better. And the first way we tried to do this was to take these notions of adjacency that we've been using in constructing these sequences and find a way to rewrite it in purely arithmetic terms so that we can generalize it further and maybe have something that's a little less unwieldy to work with. So if we pull up our original quilt diagrams again, we noted first that we have the fact that two boxes are going to be adjacent, ignoring some cases in the middle where the spiral degenerates, if and only if the difference in their indices are in these two sets. So for the Fibonacci quilt sequence, the set was 1, 3, 4. For the triangular quilt sequence, the set was 1 and 5. So the first step to maybe simplify the sequences that we would find would be to just consider the analogously defined sequence where the only difference is we define adjacency right away to mean that the difference in indices is given by these values rather than this eventual behavior we observe in both of the sequences. So now we have these Fibonacci quilt-like sequences and triangular quilt-like sequences that we would seek to better understand. And once we have this definition, it shouldn't be too hard to see that we can now generalize it to replace S with any collection of positive integers. And define the corresponding S legal index difference decomposition of some indexed collection of integers to just be a sum of some finite set of those integers where the difference in any of the indices does not lie in our set S. So this is a lot of notation to throw up at once, but if we put in an example, hopefully it will become clear. So just take your set S to be the singleton of 2, for example, and your index collection of integers to consist of A1, A2, A3, and A4, whatever those may be. Then we want to consider an S-lid decomposition to be something like A1 plus A2, where the difference in the indices is 1 and hence not an S. On the other hand, A1 plus A2 plus A3, you have an A3 and an A1. So the difference in indices is 2. So this would not be an S-lit decomposition. And then the next step, following the same constructions we use for our quote sequences, is to use S-lit decompositions to define a sequence. So the S-lit sequence consists of an nth term given by the smallest positive integer that doesn't have an S-lit decomposition using all the previously defined terms in the sequence. So we have some examples based on what we've already talked about. So the one lid sequence, for example, will just be the Fibonacci numbers. This is the interpretation of the Fibonacci numbers that we started this whole talk with. Similarly, the 1, 3, 4, and 1, 5 lid sequences will be the Fibonacci and triangular quote-like sequences. So understanding these should help us understand the recurrences in these quotes. As another example, if we take the empty set, then the corresponding lid sequence will just be the powers of 2. This can be best seen by viewing the numbers in binary, and then we see that every number decomposes uniquely where we don't place any restrictions on how far apart the index or the indices are. So these are our these are the definitions of the sequences we are going to consider. And in order to explain the results we found on what patterns these sequences share, I will pass it off to Santiago.
Hello. So the first thing we found is that for the next term in the sequence, we found a lower bound. So if we let k be the maximum of the set S, then for all I greater than or equal to k plus 2, then ai is greater than or equal to ai minus 1 plus ai minus k plus 1. The proof of this is actually very simple. By definition, all the numbers up to ai minus k plus 1 minus 1 have an S-lit decomposition using ai1 up to ai minus k plus 2. But then we can add ai minus 1 to each decomposition and obtain a legal decomposition, because the difference in indices between ai minus 1 and the terms of the previous decomposition is big enough so that it's not in S. Now, with these, we get recompositions for all the terms between ai minus 1 and ai minus 1 plus ai minus k plus 1 minus 1, which gives us that ai must be greater than or equal to ai minus 1 plus ai minus k plus 1. With this, we know that ai is equal to ai minus 1 plus ai minus k plus 1 if and only if it doesn't have an S-lit decomposition using a1 up to ai minus 1. Some sequences have this lower bound as sharp, which means that the next term in the sequence will be this lower bound. For example, this 1, 2, 4 lit sequence has a8 equals to a7 plus a3, or a9 is also equal to a8 plus a4. But other sequences, such as the 1, 5 triangle quilt sequence, are very badly behaved. So some terms follow these and some others don't. So for example, a7 is equal to a6 plus a1, and a9 is equal to a8 plus a3. However, a10 is not equal to a9 plus a4. We found that for this particular sequence, a lot of the odd terms do have the lower bound as sharp until like the 30th number or so, and the evens don't until the 30th number or so. Then it becomes kind of random which ones have this lower bound and which ones don't. Now I'll pass to my colleague Zeus. We'll talk about some other results we have.
Okay, so we saw that some sequences this equality holds and some not. So our goal is now to try to understand those in which the equality actually holds. So to prove that the recurrence holds for some certain cases, a first lemma that we use that's used for us is to bound the largest composition using the previous terms, and that's going to be similar to sum in every k minus c terms. Later we're going to define c. You're going to see how that's going to be useful. But if we add every k minus c terms, we can have a bound on that sum by a larger number in the sequence. The proof is not really insightful, is by we apply induction on L and we use the lower bound lemma that we had before. And using this lemma, which is it's very powerful later, we are able to prove that if we fix the set S to be all numbers from 1 to k and remove k minus 1. So in this case, we apply the previous lemma with c equals 1. The corresponding lead sequence will satisfy the recurrence whenever it makes sense. So for all I at least k plus 2. For k at least 8, if we do a similar thing, but instead of removing k minus 1, remove k minus 2, the sequence is gonna satisfy the same recurrence, but not right away, not in the first thing where it makes sense, and the second thing where it makes sense. And after that, it's gonna satisfy the recurrence. And based on data that we collected, we expect that for all c, if we remove k minus c from the set of all numbers from 1 to k, for a large enough k and large enough index, this sequence, it will satisfy the recurrence. And even more, another conjecture, which is even more general, if we have any finite set at t, and we remove all numbers of the form k minus c, where c is in the set t, so we remove things in the end, it's also gonna satisfy the recurrence for large enough k and large enough index. I'm gonna pass to Astrid to say it's gonna do next.
Okay. So other than these two conjectures, or I guess in those two conjectures, we have the condition that we have k large enough. And so working or assuming that our more general and stronger conjecture is true, we would like to analyze sparser sets S where we don't expect the recurrence relation to hold. And then next, we would like to understand the probabilistic behavior of S-lid sequences that are more chaotic. And an example of a more chaotic sequence would be the triangle quilt-like sequence that was mentioned in an earlier slide. And for these types of sequences, we will often have, or we have that certain strings of terms will satisfy a particular recurrence, but they will always break. And so we would be interested in looking at, from a probability point of view, how often this occurs and where they do break. And then lastly, going back to how calculating subsequent terms in these sequences is computationally expensive, we would be very interested in finding more efficient algorithms to do this. Yeah. And lastly, I'd like to say thank you to our grants from the NSF and funding from Williams College to support us this summer. And thank you very much.
All right, let's thank our speakers. Questions for our speakers? Okay.
Yeah, all right. So I'm curious, particularly about like the, so earlier today, we heard a talk about the Luca sequence and the fact that decompositions are not unique in the Luca sequence, but they are complete. So all of your sequences are complete, they can express all integers. And the result that was proved, or the proof was given earlier today, is that in the Luca sequences, 1/3 times phi plus 1 of the of all natural numbers are not uniquely expressible. So I'm wondering if for, say, your Fibonacci quilt-like sequences or triangular quilt-like sequences, if you could prove a similar result that maybe like the density of things that can't be uniquely expressed. I think this would be really interesting. I don't know. Maybe you need to talk to David, is the person who did that presentation. He knows Miller, so if you talk to Miller, Miller will know David. And I feel like that might be an interesting thing in kind of a different type of direction than the recurrences. So yeah.
Yeah, thank you for the suggestion. I also think that'd be a really interesting future direction to go. I think we are pretty close to proving our recurrence relation results that we want to. We'll definitely be reaching out to this person and hearing more about their thoughts on this problem. So thank you.
Any other questions?
I have a question. You said that you have some sequences that are not in the OAIS. Have you put them in yet?
I think that we haven't put them in yet. I think for many of the S, like pretty much all of the S, especially S that are particularly sparse, they don't seem to follow a linear occurrence. So it seems like we should probably put those in the OEIS. We've talked about it, but we haven't. Yeah.
Yeah, the OAS always needs more sequences.
We're very happy for that possibility. So, yeah.
Yes. we would.
So this part may no longer be recorded because the internet just knocked out on my laptop, which was recording this. So I have no idea what
I'm also recording this. So
So I've got to go run deal with some other technical issues. If you guys can make it here, you're welcome to join us for dinner. If not, we'll have to do it in 2 years.
all right.
Take
Thank you
care.
very much, everyone.
Thank you.
Bye.